This video is the second part of the quantum mechanical model. You should already be able to describe atoms, cations, and anions, and write configurations for the atoms that are neutral. But by the end of the video, you should also be able to construct electron configurations for sublevels of ions, including exceptions to the Aufbau, using and understanding the noble gas shortcut, and labeling atoms as dimagnetic, paramagnetic, and isoelectronic. So our question of the video is, why is iron magnetic? First, let's talk about ions. When ions form, electrons are added to or subtracted from the valence shell. So if you look at fluorine's configuration, what we'll do is add an electron to the 2p sublevel, since it's the most energetic, and make it 2p6. That would fill its shell, making it more stable, and that's why fluorine gets a negative ion. That just is the most common ion. Manganese can form many different ions because if you look, its valence shell is actually 4s2. We're going to remove electrons from the 4s because it's the highest numerical level, which means it's its valence. But manganese can also form other ions such as Mn plus 4 or plus 7, which means that it can also start losing from the d sublevel as well. So remember to lose from the highest numerical level first, and then from subsequent levels. A noble gas shortcut will be helpful when we won't really want to write out the really long configurations. It is called the noble gas shortcut because you have to find the noble gas numerically before the element. Once you find it, you put it in brackets and assume its electron configuration, or the number of electrons it has. And from there, you just add on, like Aufbau says, however many electrons you need to fill the configuration. For sodium, you can write it long, or you say neon in brackets because it's a noble gas numerically before it, and then 3s1. Neon had 10 electrons, and so the additional electron gives 11 electrons for sodium. Or similarly, sulfur, who has 16, can be written out long, or again, sulfur's noble gas before is neon, 3s2, 3p4. So this can continue and we'll practice more in class. We also have a few exceptions to the rules. So if you look at chromium, according to Aufbau, it would be given the configuration that ends in 4s2, 3d4, which if you look at the picture, would look like this: up, down, up, 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 up. But in actuality, what happens is the d block, since it's more energetic, pulls from the s electrons to fill its d block. And that way, all 6 of these orbitals have 1 electron each. Remember we said Hund's rule, where it's more stable to have up, 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 then down, down, down? Well, that's what it's kind of doing between the 4s and the 3d, but only for chromium's group. So this happens throughout group 6. It also happens throughout group 11. So if you look at copper, it should look like 4s2, 3d9, but what happens is it's unstable to have that blank in the d, but have 4s filled. So once again, it will steal from the 4s to fill its 3d. So if I just go back for a moment, when I go into the next element, instead of chromium, the next element's manganese, manganese will fill the 4s again, and then start filling after that. Iron will have it in a D, and so on. So it's just those two groups, 6 and 11, that we have to watch out for. So if we look at the configuration for gold, gold looks like it should end in 6s2, 3d9, but now we learn that d4 and d9 are unstable. So it steals from the s and fills the d, 6s1, 5d10. Technically, all the electrons are still there. We're just moving the placement. And last, our word isoelectronic. We've heard the prefix iso before, meaning that something's similar about them, like isotopes or isomers. And so in this case, it's the isoelectronic elements. They have the same electron configuration. It does not mean that they have the same exact properties, since they'll have different protons and neutrons still. But you can see that argon itself is 1s2, 2s2, 2p6, 3s2, 3p6. Potassium atom is different. No two atoms will have the same number of electrons, but the ion might. So when potassium loses its electron from the valence, it has the same configuration that argon once had. So in that case, they're isoelectronic from each other, the ions to the atoms. So again, two atoms will not be isoelectronic, but an ion and an atom can be. And multiple ions can be isoelectronic. So actually, oxide, fluoride, neon, sodium, and magnesium ions all have the same configuration of 1s2, 2s2, 2p6 because they all have 10 electrons. But you notice that their sizes are different because of their number of protons, which we'll get into more when we do periodicity. And then magnetism. Para and dimagnetic. So paramagnetic, and you should probably write about this, is when you have unpaired electrons and they cause it to be attracted to an electronic field. Dimagnetic is when you have paired electrons, or 2 electrons per orbital, and it causes it either to be repelled or we might not see any change with an electric field. So to show you some examples, silicon, when you draw out its configuration orbital notation, it has electrons in the s and the p orbitals completely filled up. In that case, it does not wind up being magnetic. Whereas with sodium chloride, originally sodium might have had an electron here, and then chlorine might have had 3p5, but that electron from sodium went into chlorines. Remember, there's a trade of electrons there in an ionic substance. And again, salt is not attracted to an electric field. But when you look at iron, when we fill iron's configuration, remember Hund's rule said up, 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 up until you go down. That causes it to have a parallel spin. All four of these arrows are going the same direction, and that would make it magnetic. So will the iron ion, so in compounds is still magnetic because ions lose from the 4s electrons level before they fall off the 3d, right? And therefore you're just losing your 2 electrons, and you still have these 4 electrons that have a parallel spin causing the magnetic field. So I think that you should always draw out your arrows to see if there's any unpaired. Parallel spin for paramagnetic means it is magnetic. Di for every one means it's diamagnetic and there is no field. At this point, you should be able to construct electron configurations using sublevels for ions and using now Bell rule exceptions. And then understand and utilize the noble gas shortcut, label atoms as di or paramagnetic, and last identify isoelectronic pairs for atoms.